Okay, I'm back, and so now we want to talk about how magnetism shows how the continents have moved around and how the ocean has spread. So we'll talk about that in here in just a moment. So before we do that, let's review what we know from lesson number 2 when we talked about the origin of the Earth's magnetic field. We said that in the center of the Earth you have the solid iron and nickel core, and then it's surrounded by liquid iron and nickel. And then as this liquid iron and nickel is going around in circles, because the Earth is going around in circles, the Earth is spinning, then that's what causes ultimately the Earth's magnetic field. So it was called a geodynamo theory. And so if we were to, let's draw a picture of the Earth, and let's tilt the Earth 23 degrees. Okay, because the tilt of the Earth is what causes the seasons. And so if we make a line that's going straight up and down, then the Earth is actually tilted 23 degrees. So this is the spin axis of the Earth, and so this would be the geographic north, and then down here would be the geographic south. And so the Earth is spinning like this, and it's tilted at 23 degrees. Okay, now I may have not mentioned it, but why? So why is the Earth tilted at a 23 degree angle? So we said that the moon formed as a collision because of a collision of the Earth with an object about the size of Mars. We also think that that collision caused the Earth to be tilted at about a 23 degree angle. And so if you look at the other planets in our solar system, you'll also notice that they're tilted at different angles, and we also think that that was due to collisions. So anyway, getting back to the magnetism thing. So you might think that the magnetic field of the Earth also comes out here and then goes in here, so that the magnetic field coincides with the geographic north and the geographic south. And it doesn't. So do you remember that inside the Earth, it's very chaotic. It's very hot. You've got materials that are going around and around like this. You also have materials that are going up and down. They're convecting. And so what that does is it twists the magnetic field inside the Earth. Well, that causes the magnetic field to move around on the Earth. So in that first picture there, that shows where the magnetic field is coming out of the Earth in the northern hemisphere. And so do you notice that if you lived in, let's say you live in Portland, Oregon, and you took out your compass, let's say it would not point north like this. So when you orient your map, normally you make the north part of the map straight up and down, but your compass needle would point in this direction over here. Now, if on the other hand, let's say you lived in the central part of the United States, well, your compass needle would be pointing this way, pretty much the same direction as the geographic north. But if on the other hand you lived over in Hudson's Bay, your compass needle would be pointing in this direction. And so where all of these arrows are coming together, that's going to be the location of the south magnetic pole of the Earth, because remember, the north end of a magnet points towards the south end of a magnet. So what we refer to as magnetic north is really a south magnetic pole. Okay, so the point is that depending on where you're at on the continent, your compass needle will point the same way. And it turns out that if there's rocks that are molten, and then those molten rocks exist today, they would have minerals in them that would point in these directions. And then when those minerals solidify in those rocks, then those rocks give you a history as to where was the magnetic pole at that time. Okay, the other one is magnetic inclination. And so if there's a special kind of a compass that allows the compass needle not only to rotate like this, so the compass is flat, it not only allows it to rotate like this, but it also allows the compass needle to dip. And that when it dips, it points into the earth. Again, it's pointing towards where that south magnetic pole is, inside the earth. And so that's called a dipping compass. And we call this magnetic inclination. And so again, that angle can be caught inside the rocks, inside the earth. It can be frozen in time. Okay, our next slide shows you that the location of the south magnetic pole in the northern hemisphere changes its location. It wanders around. Now you'll notice it always stays close to the North Pole, but you can see that sometimes it's close to the geographic North Pole, sometimes it gets close to North America, sometimes it goes over there by Russia, and so it has actually changed where its location has been over thousands and millions of years. And the reason why it's constantly wandering is because inside the Earth you have the magnetic field caused by the spin of the Earth, but it's also being affected by this convection that's going on inside the Earth, and it gets pretty complicated. You know, where does this magnetic field come out? So the point is that over thousands and millions of years, the location of the south magnetic pole changes. Okay, let's take a break, and when we come back, we're going to talk about how can the magnetic field get trapped in a rock.